Right, continuing where we had left off, we were talking about balancing equations which have polyatomic ions, so reactants and products which have polyatomic ions, and the importance of keeping that polyatomic ion intact while doing the balancing. All right, don't split it up into its individual atoms. Okay. So when you're balancing Na3PO4, sodium phosphate, AQ means dissolved into water. It splits up completely into water, into sodium and phosphate ions. And then MgCl2AQ also means that the magnesium and the chloride ions split apart completely in water. They're dissolved into water. All right, so when these two react, then these two in the middle, all right, the two in the middle come together, magnesium and the phosphate, exchange of dance partners. So it forms magnesium phosphate, which is not soluble. So that's a solid, it's a precipitate that comes out of solution. The extreme left, extreme right, the sodium and the chloride come together. All right. So how do you balance this equation? First start with the sodiums. You have 3 sodiums, so you need a 3 over here. All right. That would give you 3 chlorides. However, you have 2 chlorides. So what's the common denominator between 3 and 2? It would be 6. All right. So you would place a 3 here. Okay. That would give you 6 chlorides. That means you have to change this number to a 6. That means you have to place a 2 here. All right. So that would give you 2 times 3, 6. Okay. Then if you put a 2 here, that would give you 2 phosphates, and you have 2 phosphates on the other side. If you put a 3 in front of the magnesium chloride, you get your 6 chlorides. You put a 6 here, you get your 6 chlorides, and you get 3 magnesium, and you have 3 magnesium on the other side, and that would be the final balanced equation. Right? So 2 times 3, that's 6, and 3 times 2, that's 6. So you have a 6 in front of the sodium chloride, 2 phosphates, and you have 2 phosphates. You have to put that parenthesis around the phosphate, remember, from what we talked in the last chapter. So you get 2 phosphates, and then there's a 3 in front of the magnesium, so Mg3, 3 magnesium. All right, so now everything is balanced. Okay, so then step 4 is to finally make sure that break it down into their individual ions and see that they're all properly balanced. All right, so balance and list the coefficients in order from reactants to products for the following. So you have iron 3 oxide reacting with carbon to form elemental iron and carbon dioxide. So let's start with the iron. You have 2 of them here, so you need a 2 here. All right. And then the oxygens are unbalanced. There's 3 here, but 2 here. So what's the common denominator between 3 and 2? It would be 6. So you'd put a 3 here. Then that means you need a 2 here. All right. So 2 times 2, that would give you a 4. Okay. And so you would need a 4 here. If you put a 3 here, then you need 3 here. All right. So B would be the best answer because 2 Fe2O3 plus 3C giving you 4 Fe and 3 CO2. Okay. Coming to the second one, you have Al plus FeO giving you Fe plus Al2O3. Okay. So for this, Al needs a 2 because there's 2 Al. So 2 Al, and then there's 3 O's, so you need a 3 here. All right, so 2 Al, 3 FeO, and if you have a 3 here, you need a 3 here as well. So 3 Fe, and you don't need anything to do to this Al2O3. It'll be balanced now. So A would be the answer. 2 Al, 3 FeO, 3 Fe, and the 1 Al2O3. coming to this equation, again, you need a 2Al here to balance the Als, and then you have 3 of those sulfates, so you need 3 here. All right, so that would give you 3 sulfates. So 2Al, 3H2SO4, and 3 times 2 is 6, so you would put a 3 here as well. All right, and then you don't need any changes here with the coefficient. So it would be 2Al, 3H2SO4, 1Al2SO4, 3, and 3H2O, which would be B. All right, so we are going to talk about the types of reaction. All right, one type of reaction is called as combustion, which is it's just nothing but burning. All right, so here you see a candle burning. So it's very similar to the coal burning or the fuel, gasoline burning. All right, any kind of burning requires oxygen. Without oxygen, there will be no burning. All right. So the candle is burning using oxygen from the air. Okay, so this type of reaction where it's some kind of carbon type of source and it's utilizing oxygen and undergoing burning is called as combustion. So here are the main categories of reactions. You have combinations, where a couple of reactants combine together to give you a single product. Decomposition, where you have a single reactant breaking down into one or more products. With decomposition and combination are the exact opposites. And then you have single replacement, where you have an element reacting with a compound, and then you get a compound followed by an element. So this original element has pushed out one of the components of the compound with which it is reacting. Double replacement, as we saw with the magnesium chloride sodium phosphate reaction, is like an exchange of dance partners. All right, the metal of one compound pairs up with the non-metal, the anion of the other one, and vice versa. Combustion is, it requires oxygen. This is a burning reaction. Usually it is some kind of carbon compound combining with oxygen to form carbon dioxide and water. So the products of a combustion are always going to be carbon dioxide and water. All right, so this is a combination that you see here. You have sulfur, solid sulfur combining with oxygen from the air in a kind of combustion, although it doesn't have carbon, so therefore it's also characterized as a combination. Okay, so it's formed sulfur dioxide. Again, just like carbon and oxygen forming carbon dioxide, it's a rearrangement of the atoms. All right, so this is already balanced. Similar combinations are any kind of metal combining with oxygen to form the oxide, like magnesium with oxygen to form magnesium oxide, or sodium with chlorine to form sodium chloride, or sulfur trioxide dissolving into water to form sulfuric acid. All right, so those are all kind of combinations, and the key is that you have one or more reactants and a single product. That's how you identify a combination. So here you have a combination of magnesium, the metal, burning in presence of oxygen. So it is a kind of combustion. Heat is being provided, and you're using a Bunsen burner for the heat source, and you're forming the magnesium oxide. So this was the elemental magnesium, just magnesium atoms, and then you see the oxygen atoms coming and getting wedged in between that. All right, so you form magnesium oxide, a white powdery looking substance. So you have this shiny metal, and then as it's burning you can see that white stuff forming on the unburnt metal. Decomposition is, you have a single reactant all right? It could be a combination of two different elements, and then it splits up into two or more products, all right? So mercury oxide solid, all right? You decompose it, you heat it up, and then it splits up into the mercury, which is liquid at room temperature. It's a metal, but it's a liquid at room temperature, and the oxygen comes off as gas, right? So that is a decomposition reaction where you have just a single reactant and you're getting two or more products, all right? So here you can see that mercury 2 oxide um, getting decomposed. You can see that once you heat it up, it is breaking down and you're getting mercury which deposits on the sides of the glass. You can see a silver stuff forming on the sides of the test tube, and then the oxygen gas just dissipates into the air. Single replacement, as you can see here in this diagrammatic approach to describing single replacement, is that if this is one reactant, this is a compound, this is an element in most cases, and that element is pushing out one of the components of the compound, all right? So it's taking its place. That's why it's called as replacement, all right? So this element is pushing out this one from its compound and taking its place, and that comes off, all right? Okay, so this would be a metal with acid. Metals get corroded or eaten up by acid, so what basically they're doing is the more reactive metals are able to push the hydrogen out. So it's always element, compound, compound, and element, all right? That's how you identify single replacement. So zinc is pushing out the hydrogen, taking its place, and the hydrogen gas comes out, okay? So you can see that here in this picture, you have a nice shiny piece of zinc, and you have the hydrochloric acid, where the hydrogen and the chloride ions are separated out, all right? It's a clear solution. And then you can see that the zinc is getting eaten up. You can see the bubbles of hydrogen being formed, all right? So zinc now has taken the place of hydrogen in the solution. All of the hydrogen has come out as gas, okay? So eventually you will see that piece of zinc disappearing until it completely dissolves into the acid. Double is again exchange of dance partners. So A is going with D, extreme left to extreme right. The two in the middle are coming together, all right? So you get now two different products, all right? So metal ion of first compound goes with the non-metal or the anion of the second, and then the anion of the first goes with the metal ion of the second, okay? And so you get these two products. So silver nitrate, extreme left to extreme right, so it forms AgCl, which is not soluble in water, it comes out, and then the sodium and the nitrate stay in solution. So this is called as double replacement. So you see here copper sulfate solution. The copper and the sulfate ions are split apart, forming like, it's a clear solution, although it's blue in color. Now you put a zinc strip in that, all right? And so what do you see happening? The zinc is getting dissolved, but at the same time you see some red copper appearing on top of the zinc. So basically what is happening is zinc is pushing the copper out of solution, all right, and taking its place. Okay, so the copper coming out of the solution is depositing on the zinc that has not reacted yet. Okay, and finally you have combustion reactions, where a carbon compound is reacting with oxygen to form carbon dioxide, water, and a lot of energy. And we will stop here.